So, we move on, and this is the last segment of the course, that is the mass transfer. And in this segment, I plan to take about 12 lectures, which of course will include 8 or 9, the discussion on the fundamental parts, and 2 or 3 lectures on the application, just like the way we have done heat transfer. And we will also have about 4 or 5 problem solving sessions, depending on the time available. So, mass transfer is a very important process in engineering. You take any discipline of engineering, conventional engineering rather, civil engineering, mechanical engineering, metallurgical, chemical engineering, and mass transfer finds quite a bit of application. For example, an environmental scientist may be interested in finding out that over which area the particulates which come out of the Pankey chimney gets distributed. Similarly, a civil engineer may be concerned about effluent distribution over the area in a river because of discharge from the tanneries or other waste generators. Similarly, in metals processing industries also, and mineral engineering also, there is quite a bit of mass transfer which is involved, particularly in the manufacturing industry, which we will gradually discover in this course. Now, we know that thermodynamics tells us about the states, or if you leave a process like that, at what is the final stage or the equilibrium state in which the system is going to move to, and about that equilibrium state, the thermodynamics tells us, provided we provide the state variables. And in kinetics, basically mass transfer is one of those mechanisms. We would really like to know that if it gets to a final state, how long does it take to get to that stage? That is the kind of a question that we would like to address. As we have done in the context of heat transfer, for example, we know that if 2 objects at different temperatures, we leave them at different temperatures, after time t, both of them will attain a thermal equilibrium, state of thermal equilibrium, meaning that they will have a similar temperature. But the question that we ask in kinetics is, well, we know the state of equilibrium, which is the final temperature, which is the room temperature where 2 objects are with different temperatures sitting, but we would like to know that after how long the 2 objects are going to attain to their equilibrium temperature. Similarly, here also in the mass transfer context, there may be, instead of thermal equilibrium, we may have chemical equilibrium, as we will see, and we would like to know that because of the mass transfer processes, how long will it take for the chemical equilibrium to get established. Because temperature difference causes heat to flow. Similarly, in mass transfer, we will see that concentration difference drives the mass transport rates. And you must understand that temperature is a scalar quantity, so is concentration. So, there is going to be quite a bit of similarity between what we have studied in heat transfer to that in mass transfer, particularly in the context of diffusion and convection, or diffusive or convective mass transfer processes. So, at mass transfer, I think the classic example of mass transfer which starts in our daily life is right in the morning when we take sugar, a spoonful of sugar, and try to stir it into a cup of tea. So, that is what we are saying, that the solid, that is a solid liquid mass transfer basically, that we have solid, the sugar, and then when we put it into a cup of tea and stir it, the sugar dissolves. So, basically if you stir it, the sugar dissolves faster. If you do not stir it, then the first sip of tea is going to be devoid of sugar. On the other hand, the last bit of tea is going to be extremely sweet because it has not mixed properly. So, the homogeneous concentration is the equilibrium concentration in this particular case, which may be smaller than the saturation concentration of sugar. Okay. So, widespread application is there, and I can go on, and we will discover as we go that what are the applications of the theories of diffusion to metals and materials processing, and that will probably convince you that why should we spend about 10 to 12 lectures. And as I said, then each of the two topics that we are going to discuss a little elaborately, we have separate courses. So I will not be able to cover. For example, in the context of diffusion, it's a huge subject, and you can go to any depth possible, but that is not really necessary as far as this course is concerned. We will try to show that if you know preliminary fundamentals from an engineering sense, I am saying, of diffusion, the rate equations, etc., many engineering problems we will be able to analyze. So with this brief introduction, we will start discussing the fundamentals of mass transfer. And to start with, as we have outlined in the context of heat transfer, that we have heat transfer mechanisms essentially are conduction, convection, and radiation. And here also we see that we have diffusion or diffusive mass transfer, and convective mass transfer are the two major mechanisms. I have repeatedly introduced this term. I said heat conduction is also a thermal diffusion process. So you have momentum diffusion, mass diffusion here, and thermal diffusion. And the general feature of a diffusive process is that it obeys a gradient kind of a law. In the case of Newton's second law of viscosity, Newton's law of viscosity, we have seen how the shear stress or momentum flux is related to the velocity gradient. In the context of heat transfer, we have seen, or diffusion, conduction, we have seen that how heat flux is related to temperature gradient, and the phenomenological description of mass transfer or diffusive mass transfer, as you all know, is a fixed law of diffusion where the mass flux or molar flux is related to the mass concentration gradient or the momentum concentration gradient. So the same philosophy applies, as I said, that conduction is a very slow process of heat transfer. Similarly, here I would say that relative to convection, the diffusive mass transport is a very slow process. The property of material which causes diffusion, mass diffusion, is the diffusivity, which is synonymous to thermal diffusivity, which I have outlined in the context of heat transfer, and kinematic viscosity, which I have introduced in the context of fluid flow equation. Okay? So we have fixed law here, and it says that the flux of I is equal to, there is one-to-one similarity between the concentration gradient of I. The flux of species I in the x direction, the negative sign comes because from a higher concentration to a lower concentration. In our system, we would see that I will introduce that discussion. This concentration better be taken as activity, because when we will discuss, it essentially tells here that from higher concentration to lower concentration, material can flow. Okay? But in fact, there are situations where we can see that from lower concentration also material can flow to higher concentration, but lower concentration essentially gives rise to a higher activity. So more specifically, this should be an activity, but you do require an activity composition relationship here. But for the time being, in the first very lecture, we would consider that this to be a concentration, and this concentration could be a molar concentration, could be a mass concentration. If I say it's a mass concentration, then I would say it is kg per meter cube of I, okay? Kg of I per meter cube of the solution. And if it is a molar concentration, then moles of I per unit volume or per meter cube of the solution. And this is the flux in the x direction, and this is the x coordinate, and d represents the diffusion coefficient of the species I in the medium under consideration, because where the material is I is diffusing, it must be diffusing in a material. So typically people write that dij, which essentially means that I is the species which is diffusing through J. Okay? So that sort of a notation can also be introduced, and that is on the left hand side is the flux. Typically, as I said that okay, let me just introduce this expression. Similarly, in convective mass transfer, we have the mass flux given in terms of a mass transfer coefficient times the concentration gradient. So, differential concentration. So, delta C is not concentration gradient. So, just like the way we have defined heat flux is equal to, so I would say this is the convective mass flux, this is the flux notation. When you say we write volumetric rate of heat generation, this double prime becomes triple prime, which essentially means one length scale more. Okay? So, this dot essentially means it is the rate, and this double prime essentially implies that it is a per unit area. So, it is moles per unit time per unit area, or mass per unit time per unit area. So, similarly, this is the flux of I, and this is the concentration differential. So, it is an analogous expression too. So, this is our rate law, and the same sort of a discussion that we have made in the context of convective mass transfer. We will also do the similar continue with the discussion when you come to this chapter, but for the time being, this Fick's law can be taken as the phenomenological description to address diffusion processes, and on the other hand, convective mass transfer via a mass transfer coefficient. We will encounter our knowledge of heat transfer will come very handy here. For example, the mass transfer coefficient will be obtained. We are also is going to have here a free convective mass transfer and a forced convective mass transfer, just like the way we had free convective heat transfer and free convective forced convective heat transfer. Just like the way temperature gives rise to a density differential, similarly concentration also will give rise to a density differential. For example, you know that when you have a blast furnace hot metal, which contains about 4% carbon, into which when you put solid steel scrap, what happens? The steel scrap goes to the bottom of the vessel and settles down, because the blast furnace hot metal is much lighter than the scrap. Scrap does not contain much carbon, but the blast furnace hot metal contains about 4–5% carbon, as a result of which its density is lighter. Scrap is heavier. So, scrap added into the blast furnace hot metal will settle to the bottom. So, therefore, we understand that with the carbon content or with the various kinds of solutes, the density can change, and as a result of which also solutal free convection, thermal free convection we have studied, we will study here later on solutal free convection in the context. But nonetheless, on the basis of this two formulation, we should be able to address diffusive and convective mass transfer processes. Before I proceed further, I want to tell you that we have several units possible, that we have. If you say flux, the flux could be either a mass flux or a molar flux. These are the options before us. Similarly, the concentration can be used. For mass flux, we can have mass concentration, which is or we can have mass fraction. This is also possible. Similarly, molar flux, we can have molar concentration and we have mole fraction. Mass concentration will have a unit of kg per meter cube. Mass fraction does not have a unit. Molar concentration will have a unit of moles, and that moles essentially, because we do SI units, so it means it is not gram moles, but it is kg moles. Okay. Similarly, accordingly, the mass flux could be kg per meter square per second, or molar flux could be kg moles per meter square per second. And if you write this, for example, if this is my typically n is represented, okay, our notations are basically, when you do write capital J, we essentially imply the capital J is the notation for mass flux and n is the notation for the molar flux. So, we can say, let me just, because I am going to introduce another one. So, you can say that this is small j, and this is molar flux, and this is the molar flux. So, let us, because I am going to introduce another parameter later on. I just changed the notation because n will be used in other to represent something else later on, as I will say. So, capital J is for mass flux and small j is for molar flux. So, if this is molar flux and this is the concentration, molar concentration, then this can be also written as dI into C mole fraction, where capital Xi represents the mole fraction and C represents the molar density of the solution or the mixture. That is also a possibility. Okay? So, if you write it in terms of mass, then what happens is this becomes mass fraction and this becomes the density of the solution or the medium. Okay? So, that is also possible. So, these are the possibilities for us. We have 4 different types of units can be used, 2 different types of units can be used for mass fluxes, and in this course most of the time we will use in this discussion the molar flux, but you know that the mass flux and the molar fluxes are interconvertible. So, there is no issue at all, but I wanted to be certain. Note down the notations. Okay? So, C molar concentration, I would say this is denoted by C and this is by X, and similarly the mass fraction is M, and then this could be given by 1. But this we are not going to use, as I said, that this is capital X. So, this is not to be used in this particular course. So, the molar concentration will denote by C, the mole fraction will denote by capital X, small x will be our direction vector, and then the small j will be used to notate, express the molar, and this we will call, when we deal with diffusion phenomena, we will call molar diffusion flux. We will read it like molar diffusion flux of I along x direction is equal to negative of diffusion coefficient of I in the medium into concentration gradient of I along the x direction. So, that is how we are going to read it. Now, the treatment of diffusion in a gaseous medium and the treatment of diffusion in a solid medium are slightly different. We will first talk about the diffusion process discuss now diffusion. And as I said, on diffusion one can take a full-fledged 40 lecture course, but we will not go into the depth. We will only introduce those essential elements which would be necessary to address problems of practical interest as applicable to metals and materials processing. Now, at this stage, as we proceed to discuss diffusion, I would isolate the diffusion with respect to solids, and there we say it is a motionless media. And gases. There are subtle differences, because in gases diffusion takes place in solids, but we will see that there is not a bulk motion imposed. For example, when you have gases, you can imagine, I will just to explain this to you what I mean to say. Suppose you have a gas, okay, and you seal it, and there is another gas B, and suppose what happens is that the gas B is heavier than that of gas A. Now, when you take away this partition, what happens, because of the concentration gradient, okay, and because B is heavier than A, so that means A is lighter than B. So there is now a concentration difference of A between this point and this point. So the concentration here is a very large concentration, the surface concentration, and on the other hand, far away, the moment I have removed this partition, the concentration here is 0, so there is a higher concentration, lower concentration, so there is a diffusion is going to take place. But similarly, the reverse is going to take place with B. Okay? The concentration gradient of B is in the reverse direction because of the fact that B is a higher concentration here and lower concentration here. So A moves in the diffuses in this direction, B diffuses in the opposite direction. But because B is density of B is greater than density of A, so as a result of which what happens is B has a natural tendency, mass movement, or which we say is the bodily transport of B in the downward direction, because it is heavier than that of A, and A as a result of which tends to light up. So even though because of the diffusion concentration gradient A is diffusing, there is going to be some effect of this mass movement of the gases. So you will, if you just find out, for example, if you try to find out that how much time it takes from here to here, you cannot do it purely on the basis of diffusion, because of the simple fact that there is going to be bodily transport effect also superimposed on this diffusion, and that is why the diffusion laws, the fixed law is applicable here, but a different, we have to compartmentalize that what is the bodily transport, what is the diffusive transport, and then address the diffusion process. And that is why I said that we will address the diffusion, we will do the same shell balance, we will apply the same fixed law, but the derivation of the equations etc. for gases are going to be a little bit different because of this particular aspect. Okay? The gases, the diffusion is much more rapid than in solids, it is much more slower process, and there is no such bodily transport when diffusion takes place within the solid. So this is per se a motionless media. There is, of course, if you say that you have a diffusion coefficient D, okay, of a species I, and you have, for example, the diffusion takes place over a distance of L. In that case, you can say that L square by D represents a time scale. This is meter square and this is meter square per second. This represents a time scale which tells you that for how long by diffusion the species A will take to reach from here to here. But when you have bodily transport, this condition is not going to be met, okay, because there is a bulk motion superimposed on this diffusion process. Similarly, you can say that there is a diffusion velocity. We can say V sub diffusion, and that diffusion velocity could be something like if you take diffusion coefficient and divided by L, and this that represents the diffusion. So it is meter square per second, and this is divided by meter. Okay, so you change it, you get and this becomes the diffusion velocity. It's a pure diffusion velocity, but in this particular case, if you measure the velocities with respect to a fixed frame of reference, you will not get a matching with this, because the bodily transport of the gases are camouflaging to some extent the diffusion processes. So that warrants that the gases will need some kind of a different treatment. So we will first discuss the process diffusion in solids, and then we will talk about diffusion in gases. Diffusion in solids are extremely small, and just like the way heat conduction takes place because of the property of the solid, which is a thermal conductivity and which is an intrinsic property, structure sensitive property. Similarly here also, as we have seen, that the mass diffusion or matter diffusion takes place because of the property which is called diffusion coefficient. Now in solids, diffusion takes place, you all know, which of course we are not going to address very extensively in this particular course, but you must have in the physical metallurgy course studied that diffusion takes place because because of vacancy migration as well as interstitial. So the diffusion takes place, the mechanism of diffusion, because you can imagine that if all the lattice sites are occupied, there is no scope for diffusion. So it is, there are vacant sites, there are vacancies already available within the crystal structure, and it is because of either because of this vacancy diffusion or interstitial diffusion, the diffusion really takes place within a solid. That you all know. We will talk about a little bit about this when we talk about grain boundary diffusion as opposed to bulk diffusion later on. Now, the species, so this diffusion coefficient, okay, and it happens also, that by atomic jumps which occur over very small distances. So the process is, the diffusion process is very slow because it is an atomistic process. On the other hand, whatever I have written about the convective mass transfer, if you want to transfer, for example, material over a large distance, you have to have good amount of studying, good amount of fluid flow. You can imagine that, in your house, when, for example, you burn an incense stick, okay, and if there are fans, etc., going on in the house, you will get that aroma very quickly. Okay. On the other hand, on a stagnant day, where there is no fan, no convection current within the house, it takes an immensely long time for the incense smell to spread over. And incense smell, spreading of incense smell is nothing but, transport of materials, the gas diffusion process, and gaseous molecules from one room get transferred, and that's how we get the aroma, we get the flavor. So therefore, if you want to transfer material from over a large distance, you have to take resort to convection, and diffusion basically takes place. So through diffusive property, which is diffusion coefficient, and this jump processes, as you all know, is a thermally activated process. So we have a relationship something like d is equal to d0 exponential minus q by RT, in which q represents the activation energy of the diffusion process. So that is the relationship. It is a very strongly sensitive parameter to diffusion coefficient is strongly sensitive to the temperature. If you increase temperature, the diffusivity could be substantially increased. So if you draw this, then we have the same kind of a graph, that we have higher concentration, which is C1, I would say, and this I would say as C2, and the gradient of this, it need not be a straight line, but I have drawn it to be a straight line, that it varies as a straight line, which of course we know that it will come out when we will do energy balance, mass balance, etc., and derive the governing equations and apply a one-dimensional solution. A straight line will follow, and the gradient of this will become a measure of the flux itself. Now, based on the Fick's law, so D is a state property. If you keep the temperature fixed, the diffusion coefficient is going to be fixed, and D is a strong function of composition also. As I said, it is a structure sensitive parameter. It will depend on composition, it will depend on what is the structure, what are the defects, etc., and it will of course depend on the temperature. So knowledge of diffusion coefficient, you must understand that if temperature is changing, so does the diffusivity, and that makes diffusive mass transfer process related to the simultaneous heat transfer, and then the diffusive mass transfer process becomes coupled with the heat transfer. Okay? So I hope you understand that particular point, that what I mean to say is that since diffusion coefficient is a function of temperature, okay, so if the system is non-isothermal, temperature is changing, so it is understood that if the temperature is changing, so does the diffusion coefficient, and so is the diffusive flux. So as a result of which the diffusive mass transfer tends to be related to the heat transfer process, and it becomes a case of simultaneous heat and mass transfer. We will study this when we talk about application of mass transfer and heat transfer theories to materials processing later on. We can have now the same kind of mass balance over a control volume. We take a control volume in Cartesian coordinate, if this is the origin, and this is basically A, this is B, and this is basically C, and this is X, this is Y, this is Z, and this is the origin. So, you can take a control volume and then we can perform mass balance, how much of mass is going in. So, we know the flux expression, flux multiplied by the area is the rate at which the mass is getting in, kg per second or moles per second. The moment you multiply the flux with the area, it gives us the amount of material which is getting in. Similarly, if you take this phase and multiply the flux with the area, we will get what is the mass which is going out. If the control volume is small, we can perform linearization, and then we can arrive at a differential equation just like the way we have done it for heat conduction case. In heat conduction, if you remember and revise, look back at your notes, then the net rate of heat accumulation was written as volumetric rate of heat. That is the equation that we derived when you talk about conduction heat transfer. Exactly the same thing we did. We took a volume element, okay, which has a dimension. In this case, of course, A is equal to delta x, B is equal to delta y, and C is equal to delta z. That is the small control volume. Okay. So, delta x, delta y, delta z. That is what it implies. And that is when we apply the linearization. I have explained that what is meant by linearization, Taylor series expansion. We retain only the first term and we do in 3 different directions, mass coming in, mass going out. In this case, what we did, heat coming in, heat going out, heat coming in, heat going out, heat coming in, heat going out. And the balance of it is net rate of accumulation plus heat generation is equal to heat accumulation. Exactly, and this is in the compact form we wrote this equation as for constant thermal conductivity, if you do the same thing, because there is 1-to-1 correspondence, Fick's law vis-a-vis the Fourier's law. Okay? There is a scalar transport of temperature, and now you have a scalar transport of mass. Okay? And therefore, looking at this, if you perform the same thing, mass coming in and mass going out, take shelter under Fick's law, multiply the flux with the area, do linearization, assume that delta x, delta y, delta z tends to 0, the control volume is small, and then we can have an equation something like and in this case we will say that because it is mass moles, so we can say that the notation could be written as small c, okay, and then in which the small c essentially represents the volumetric rate of I generation. Okay, because it is molar concentration, so we will write it N, Ni. Where Ni dot triple prime essentially represents the volumetric rate of generation of the species I in that control volume. Exactly the same equation. And this equation, as you all know, if it is a steady state and no source term is there, no mass generation is there, how could mass be generated? Just like the way heat could have been generated in a control volume because of a chemical reaction, so mass can also be generated because of a chemical reaction here. Okay? And if you have no chemical reaction, no mass generation, steady state process, and then we have for, and this is our Laplace equation, as we all know, applicable to the steady state, and the one dimensional form of it is basically and the solution of this subject to fixed boundary concentrations is this particular profile which I have drawn already, and this we have discussed at length when we are talking about. So, the steady state solution in one dimension forms a straight line, as you can see here. For example, the concentration is going to be Ci is going to be is equal to A, okay, multiplied by x plus b. That is the concentration profile, the solution. And these two concentrations are found out, that as I said, x is equal to 0, Ci is equal to C1, x is equal to L, Ci is equal to Cl. In that case, I will make this Cl, and I will say that this represents my so that's how the concentration goes here. This is, and this distance essentially represents what is. And if we draw this picture, so we have a one dimensional slab in the x direction, the span length is and this is C1 and this is Cl. That is what it is. So, the two this constants of integration are found out by applying the boundary conditions. Now, if you remember, say the discussion now needs to be concerned about how do you know the concentration at the surface. In the case of heat transfer problem, the corresponding case used to be the given temperature boundary condition, that at x is equal to 0, we said T is equal to, there is no Ti or anything like that, because we will be talking about, we are not talking here of self diffusion, we are talking about diffusion of a species through a medium. So, that is why we are talking about Ci. So, in the context of temperature, it is just one single temperature, it is a homogeneous phase. T is equal to T1, and that T1 is to be a measured temperature, known temperature, which has been given to us. In this case, this tells us that concentration at this particular point is needed. How can you determine the concentration? Okay, that becomes a very important exercise here. So, it is a very tedious exercise, but typically in the context of determining the surface concentrations, we will take resort to the underlying theory, that what is really happening, understand the process, and then see that whether the concentration can be given or derived from certain theoretical considerations. Imagine, for example, I have the slab here as a steel slab. This needs to be followed very carefully. So, and that it is embedded in a gas mixture. So, it is a gas carburizing process basically. So, you have a CO-CO2 mixture, and the entire thing is steel is at a homogeneous, and then I pass the CO-CO2 mixture in such a way that at the solid, what happens is CO2 decomposes into C, and then CO2, sorry, 2CO is equal to CO2 plus C. So, this is also gas. That is the reaction. A mixture, a correct mixture of CO, CO2 is passed in such a way at a certain temperature that at the surface, this reaction I want to carburize. So, I want to have a carbon rich layer here. I want the carbon from the gas phase to get diffused into the solid, and that is how the carburization takes place. So, I have created the condition, I have created the gas composition in such a way, I have used a temperature which is a desirable temperature such that this reaction gets facilitated at the surface. So, how does really the carbonization process starts? So, therefore, this reaction must be taking place first. The gas is coming in, there is no carbon available anywhere. The gas comes in and it flows past the solid, and this reaction takes place at the surface. The moment this reaction takes place, carbon, where does the carbon stay? The carbon is now at the surface. So, it is not in the gas phase, but this carbon gets dissolved in the solid. Okay? It is the surface concentration, it is in the still phase, and that is why this notation essentially implies that it is in the matrix of steel. That is this concentration. Now, and then once it comes, carbon is in the dissolved state here, and if this concentration, the bulk concentration, is much smaller than the surface concentration, then I have created a concentration gradient over this particular distance, and as a result of which carbon from a region of higher concentration will try to diffuse inside. Now, so therefore, the diffusion process, okay, the carbonization process can be split down into two steps. One is this particular chemical reaction must take place at the surface, and first then the carbon must be dissolved in the metal. This is the first step, availability of carbon, to make carbon available at the surface. And once carbon is available, then the diffusion process, they are interlinked. If one of them is stopped, the other will not take place. Suppose if I say that I change the temperature in such a way that this reaction is no more feasible, there will be no carbonization in the whole process. So, these steps are working in series. There is one which is a chemical reaction, and once chemical reaction, following chemical reaction is the pure diffusion, and the diffusion through solid. So, of these two steps, because typically metallurgical operations are done at high temperature, it is assumed that this chemical reaction operates close to equilibrium. Okay? Diffusion is not under equilibrium, diffusion is taking place because there is a difference in concentration. It is trying to make everything same concentration, so the diffusion process goes on, but the chemical reaction is assumed to be at equilibrium. And the justification for assuming the chemical reaction to be under equilibrium is that temperature is high, and in high temperature the rate of the chemical reaction is going to be very, very rapid, and we all know Arrhenius rate law is applicable, where it says that rate of a chemical reaction is proportional to exponential rate of a chemical reaction. If you increase the temperature, it's extremely fast, and a fast process will reach equilibrium very fast. So, it is not absolutely out of place to assume that this chemical reaction, once the process starts, within a very short time will operate close to the equilibrium. What happens if this operates close to the equilibrium? Suppose we have fixed temperature, we have kept carbonization temperature same, and we have pressure also, which is P total, and this P total is equal to 1 atmosphere. So, everything is carried out not on a high or a low pressure chamber, but it is being carried out under normal atmosphere, where the total pressure is equal to that. The entire enclosure is containing or contains CO and CO2. So, I would say that this condition therefore applies. There is no other gas, no air, or no oxygen, no nitrogen. It is the furnace environment is completely filled with carbon. So, this relationship. If you look at this, then what happens is I can write the equilibrium constant. That equilibrium constant of this particular reaction K equilibrium will be written as in terms of PCO2 square, PCO square, PCO2, and to concentration of carbon in the metal phase. So, it is a activity, I would say, what sort of a scale. So, you can say Henryan activity of carbon in steel. And we know that this could be taken to be is equal to also under certain condition weight percentage of carbon. Now, we have, because the gas is coming, so we have here I have used a cylinder from where CO2 is mixed, maybe 40% is CO, 60% is CO2, and that is I am sending it into the furnace. So, that 40% to 60% is going to be available right in the to the interface itself, because I have assumed that there is no resistance to the flow of the gases within the medium, whatever I am putting at the inlet, that the entire gas mixture is available in this particular close to the interface itself. Okay? So, truly speaking, there is going to be a boundary layer, but that boundary layer, concentration boundary layer, I am not taking into account, because that is not a step. I am saying that the intensity of agitation in the system, the gas is being pumped in at a good rate, there is good amount of agitation, so the boundary resistance really does not matter. So, whatever is the at the inlet, whatever is the concentration of CO2 or the CO2 ratio, that ratio prevails right up to the interface. There is no resistance, there is no drop. So, therefore, I would say PCO by PCO2 inlet, this ratio, which may say alpha, and this is now known. The equilibrium constant, we have 3 unknowns here. Okay? I want to calculate this Hc as far as this equation is concerned. K equilibrium is known the moment we know the temperature, because delta G is equal to minus RTL and K equilibrium. Delta G value for this is known to us the moment temperature is given. So, therefore, we have 1, 2, 3 unknowns, and we require now 3 equations. One equation comes here. So, this is equal to a known parameter. The second equation is PCO by PCO2 is equal to a known parameter. The third is PCO plus PCO2 is equal to 1 atmosphere. So, if you use this constraint and substitute the value of PCO, PCO2, the surface concentration can be found out, which essentially tells us that under the condition, if chemical reaction, because most of the time we will see that in our system, in a metals processing system, mass transfer takes place, and the mass transfer leads to chemical reactions, or a chemical reaction happens, then product gets transferred from one place to another place. So, there is always a chemical reaction in metallurgical systems, and we will see, we will assume all the time that the chemical reaction per se is operational or is operating very close to the equilibrium, and that equilibrium or chemical equilibrium or interfacial equilibrium, in this case the gas solid interfacial equilibrium, will allow us to determine the concentration. Look at, for example, a similar example. This is very interesting. I do not know in how details you have studied metallurgical kinetics, but these are called determination of rate limiting steps, intrinsic kinetic steps in the process, and based on that analysis one should be able to find out that which controls the rate, and in this case the diffusion is controlled. Because the diffusion is occurring, the chemical reaction is not controlling the rate, so the chemical reaction is taken to be account. Suppose you have a liquid here and you have a oxygen bubble, and from that the oxygen is getting diffused into the liquid. So, it is a dissolution process, and there is a transport. So, this is, you can imagine that I have a container here, and oxygen is injected, and as a result of which the oxygen bubble from oxygen, the oxygen gets dissolved, and that oxygen is, because there is a starting maybe here, and that oxygen in the system is getting distributed. Okay? So, what is the process here? The dissolution of oxygen. So, it is first this reaction which takes place. Oxygen is injected gas, and that oxygen gets dissolved into metal. Once this happens, then only the oxygen is available in the liquid, and then the dissolved oxygen moves from one location to another location in the system. That is how the transport takes place. Okay? Now, you can, so you can, this gas now, this reaction, what does this reaction takes place? This reaction takes place at the gas liquid interface. So, from the gas liquid interface to the bulk, the difference in concentration gradient can be found out, provided this concentration is known to us. This concentration, which is dictated by the chemical equilibrium of this. So, the moment we say that PO2 is equal to 1 atmosphere, okay, it is a pure oxygen bubble, or if you are using air, then it is PO2 is equal to 0.21. Okay? If you know the partial pressure of oxygen, the dissolved oxygen concentration can be calculated. calculated. So, what I mean to say that in the dissolution process, you can say that the concentration of oxygen in the system is not really controlled by the dissolution of oxygen, but it is controlled by the dispersion of oxygen. The stirring in the system determines that whether it is going to be transported from one region or how effectively it is going to be transported from one region to another. And in this case, what happens is we can assume the equilibrium of the interfacial chemical reaction, and this interfacial chemical reaction will allow us to specify the surface concentration at gas to liquid. In leaching operation, for example, you have a solid, and then the solid gets transported to the liquid, and in the leaching what happens is that we have one solid X which is in the solid state, and then it gets dissolved in the liquid, and then after dissolution the transportation takes place. So, it is solid, and when it is say dissolved, that means it has, this is the solid liquid interface. So, if you draw a line like this, that is the solid liquid interface, and by this the X has gone into the liquid and then the transportation starts. And then, so we can say that look, per se this chemical reaction, we can also postulate that there is a boundary layer, and the transport over the boundary layer is the rate limiting step, okay? And so therefore the chemical reaction can be taken to be equilibrium, and particularly when leaching takes place at high temperature, high pressure to expedite the rate of leaching, this is a reasonable good assumption that the chemical reaction which takes place at the interface can be taken to be. So in the calculation of heat and mass transfer rates, when we will require, be it even in the case of convective mass transfer problems, in the case of diffusive mass transfer problems, when an interfacial concentration will be necessary, most of the time that interfacial concentration will be obtained by considering chemical equilibrium of the relevant equation which is taking place at the interface. We will continue with the discussion.